Universal scalability law matters because scaling is where intuition often fails. A team adds servers and expects twice as much traffic capacity. At first, it works. Latency drops, throughput rises, dashboards look healthy. Then the next servers help less. Then they barely help at all. Eventually, adding capacity can make performance worse. That is when the universal scalability law becomes useful. It gives performance engineers a practical way to answer one expensive question. If we add more resources, how much more work will the system actually handle? Not in a perfect benchmark. In the real world, where databases lock rows, services wait on queues, caches expire, threads coordinate, and network calls collide, the Universal Scalability Law, or USL, models how systems scale as concurrency increases. It explains why growth is not always linear, why bottlenecks appear, and why some architectures collapse after a certain point. The core idea is simple. Scalability is limited by two forces. The first is contention. Contention happens when multiple workers need the same shared resource. A database connection pool, a lock, a message queue partition, a CPU cache line, a configuration service, or even a human approval step. When contention rises, workers wait instead of doing useful work. The second is coherence. Coherence is the cost of keeping workers coordinated. The more nodes, threads, or processes you add, the more communication may be needed to keep state consistent. This can appear as cache invalidation, consensus, replication lag, distributed locking, or microservice coordination. Contention makes growth flatten. Coherence can make growth reverse. That is why USL is powerful. It does not just say there is a bottleneck. It helps estimate how severe the bottleneck is and where scaling stops being worth it. The universal scalability law is usually written like this. C of n equals n divided by 1 plus alpha times n minus 1 plus beta times n minus 1. C of n means relative capacity when concurrency is n. If one worker handles 1 unit of work, C of n estimates how many units n workers handle together. N is the level of concurrency. It might mean threads, users, processes, service instances, containers, CPU cores, or nodes. Alpha represents contention, time lost waiting for shared resources. Beta represents coherence, time lost coordinating between workers. If alpha and beta were both 0, scaling would be perfect. 10 workers would do 10 times the work. 100 would do 100 times the work. Real systems almost never behave that way. Imagine a checkout service. At low traffic, one application instance handles 100 orders per minute. The team adds instances behind a load balancer. With 2, they expect 200. With 4, 400. At first, performance looks good. 2 instances handle about 180 orders per minute. 4 handle about 300. Not perfect, but acceptable. Then 8 instances reach only 420. 16 reach 450. 32 drop to 430. Without USL, people argue about symptoms. Maybe the cloud instances are too small. Maybe the database needs tuning. Maybe the load balancer is uneven. Maybe the code is inefficient. With USL, the curve says adding instances initially helps, then contention dominates, and at higher concurrency coherence or coordination overhead becomes expensive enough to reduce total capacity. Now the conversation becomes precise. What shared resource are all instances waiting on? Is every checkout writing to the same inventory table? Is there a global lock-around coupon validation? Are all requests calling the same payment gateway synchronously? Is every order forcing a cache update across the cluster? USL does not replace investigation. It focuses investigation. So how do you use it in practice? Step 1. Choose what N means. Be specific. Do not say scale. Say, we are testing throughput as we increase application instances from 1 to 32. Or, we are testing transactions per second as concurrent users increase from 50 to 2,000. N must represent the thing you are changing. Step 2. Choose the capacity metric. For a web service, this might be successful requests per second at a fixed latency target. For a batch system, jobs completed per hour. For a database-backed workflow, confirm transactions per minute. Measure useful work, not just activity. A system producing more errors is not scaling. A system increasing throughput while latency becomes unacceptable is not scaling in the way users need. Step 3. Run controlled tests. Measure capacity at several values of N. 1, 2, 4, 8, 16, and 32 instances, for example. Keep the workload stable. Keep the request mix consistent. Warm up caches. Avoid changing multiple variables at once. Each data point should answer. At this concurrency level, How much useful work did the system complete? Step 4. Normalize the results. If one instance handles 100 requests per second, that is the baseline. If 2 handle 180, relative capacity is 1.8. If 4 handle 300, relative capacity is 3. Normalization makes scaling curves easier to compare. Step 5. Fit the USL curve. Estimate alpha and beta from measured data. Engineers use spreadsheets, R, Python, statistical tools, or performance modeling packages. The tool matters less than the discipline. You are fitting a curve that explains how capacity changes as N increases. Then study the shape. If alpha is significant and beta is near 0, the system mostly suffers from contention. More workers help, but each new worker helps less than the previous one. If beta is significant, coordination overhead grows with concurrency. This is more dangerous because capacity can peak and then decline. Step 6. Find the knee of the curve. The knee is where adding resources still works, but returns drop fast. Beyond it, cost rises faster than capacity. In cloud systems, this is where autoscaling can become wasteful. Step 7. Use the model to guide engineering decisions. If contention is the issue, reduce shared weighting, split hot database rows, increase partitioning. Remove global locks, tune connection pools, use asynchronous processing, cache carefully, separate read and write paths. If coherence is the issue, reduce coordination. Avoid unnecessary distributed transactions. Minimize cross-node synchronization. Use local state where safe. Relax consistency when the business allows it. Design ownership boundaries so fewer services must agree on every request. Consider a database connection pool. A team scales an API from 2 containers to 20. CPU is low, but latency rises. USL shows strong contention. Investigation reveals every container shares the same small database connection pool and request queue for connections. The fix is not simply more containers. It is right-sizing the pool, reducing slow queries, adding indexes, and separating read-heavy from write-heavy traffic. Consider a flash sale. Every order updates the same inventory record. At first, more workers process more orders. Then throughput flattens because transactions serialize around one row. USL identifies contention. A better design might reserve stock in partitions, use optimistic concurrency, queue inventory adjustments, or redesign the sale flow so every request does not fight for the same record. Consider cache invalidation. A content platform adds service nodes. At moderate traffic, performance improves. At higher node counts, every content update triggers invalidation across the cluster. Nodes spend more time coordinating cache state, that is, coherence overhead. Improvements might include scoped invalidation, clearer ownership boundaries, version cache keys, or accepting slightly stale reads where the product allows it. The biggest mistake with the universal scalability law is treating it as magic. It is not magic. It is a lens. It helps you move from vague statements like, the system does not scale, to measurable statements like, capacity peaks around 16 workers because contention and coordination overhead dominate after that point. That difference matters. It changes capacity planning, architecture reviews, incident analysis, and cloud spending. It gives engineers a common language for explaining why more hardware is not always the answer. Used well, USL helps predict whether scaling out will help, estimate where returns decline, identify whether contention or coordination is the bigger problem, and decide whether the next investment should be infrastructure, code optimization, data partitioning, or architecture redesign. So the next time someone says, just add more servers, pause. Ask what shared resource those servers will fight over. Ask what coordination they will require. Ask where the scaling curve bends. Because scalable systems are not built by adding capacity blindly. They are built by understanding the forces that limit capacity.